Alright, this is Hamza Beg, and this is my AP Physics 1 final project. So the first situation that we're dealing with comes from a game called Forza, which is a free roam car racing game. And the first situation is that a Ferrari is traveling at 30 meters per second on a cliff that is 60 meters tall. It drives off the end of the cliff, and we need to find the time it takes and the distance that the car will land from the base of the cliff. So here is your video. Alright, so this situation deals with projectile motion because the car is essentially thrown off the cliff, and it follows the format of projectile motion with related vertical and horizontal motion because of a common time. And the only force that is acting on the car as it drives off the cliff is the force due to gravity. So we start by using x equals x initial plus velocity initial times time plus 1/2 acceleration times squared. And we can initially find the time it takes for the car to land using the vertical components because we know more of that information. So we get 3.5 seconds. And then we can solve for the horizontal distance using that time plus the other information that we already knew. So we end up with a time of 3.5 seconds and a distance of 105 meters from the base of the cliff that the Ferrari will land. So this next situation is a Mazda Miata of 1,062 kilograms is at rest on a level road with a coefficient of friction of 0.7. So this Miata in the front is at rest, and the road has a coefficient of 0.7. And then another Miata comes from the back and hits this first one at rest with a force of 3,000 newtons. And we need to find what the acceleration of the Miata will be after it has been hit. So this problem deals with forces and friction because of the conservation of energy and force that transfers from one car to another. Friction is involved because it removes some of the energy that would have been transferred from the first car to the second car, and that causes the second car to not move as fast as the first car would have. So we end up having to find a net force of the applied force, which is 3,000 newtons, minus the frictional force, which we calculated using the normal force times mu, and we get 743.4. And then we can set that equal to mass times acceleration because force equals mass times acceleration. So when we subtract these two values and divide the mass, we end up with an acceleration of 2.125 meters per second squared. The third situation involving Forza is a Ford Raptor that is traveling along a frictionless road. And one of the wheel and tire systems has a mass of 44 kilograms and a radius of 0.4364 meters. And the wheel has a tangential velocity of 20 meters per second, and we need to find what the rotational kinetic energy will be of the wheel and tire. So here is a video of the problem. Okay, so this situation is rotational motion because we are trying to find the rotational kinetic energy through the relationship between linear values and rotational values. So we have certain linear values of 20 meters per second, and then we have a mass which is 44 kilograms, and we can find the rotational velocity from the linear velocity by dividing it by the radius. So we take 20 meters per second divided by the radius, and we get 45.83 radians per second.
Just to note, the equation with omega equals velocity divided by radius, it's supposed to say 20 meters per second divided by 0.43464 meters. The multiplication sign is an error.
And then we can find the moment of inertia of the wheel and tire by taking the mass, which we know is 44 kilograms, and multiplying it by the radius squared. So we get 8.36 kilograms times meters squared. And then we can take both of those values and find the kinetic energy, which is 1/2 I omega squared. So we plug in 8.63 and the 45.83 radians per second, and we get a kinetic energy of 8,779.63 joules. So the next situation that we deal with is a roller coaster. It is Montezuma's Revenge, which is at Knott's Berry Farm. So the first one is the roller coaster has a kinetic energy of 1,468,750 joules and a mass of 4,700 kilograms. And we need to find the apparent weight of the roller coaster at the bottom of a 23-meter loop. Okay, so this is an apparent weight situation because the roller coaster is traveling inside of a 360-degree vertical loop, and the fictitious centrifugal force causes the coaster to appear heavier at the bottom as that centrifugal force pushes outwards from the middle of the loop. So we can calculate the apparent weight using the apparent weight equation, and we have the weight of the roller coaster by taking the mass, which is 4,700 kilograms, and multiplying it by the force of gravity, 9.81 meters per second squared. And then we can take the mass again, which we already know is 4,700 kilograms, and multiply it by the velocity. And the velocity we calculated by taking the kinetic energy, which is a known, of about 1.5 million joules. And then we can solve for velocity as kinetic energy equals 1/2 mass times velocity squared. So we get velocity equals 25 meters per second. And then we put that into the apparent weight equation. So we get the mass, 4,700 kilograms, times 25 meters per second squared. And then we divide that all by the radius of the loop, which will be 11.5 meters because it is known that the diameter is 23 meters.
Just to note, in the apparent weight equation, we are adding the weight and the mass velocity squared divided by r because we are trying to find the value at the bottom of the loop. So the roller coaster should be heavier, which is why we're adding as opposed to subtracting if the roller coaster were at the top of the loop.
So we end up with an apparent weight at the bottom of 301,571.7826 newtons. And this kind of seems like a big value, but it's actually pretty reasonable because if we were to convert that into kilograms, it's about 31,000 kilograms. And that's about 6 times greater than the initial weight of 4,700 kilograms, which can be expected because the average g-force experienced in a roller coaster is anywhere from 2 to 6. And this situation is ideal without any friction, so it makes sense that the g-force would be near the upper limit of what roller coasters have. So the second roller coaster situation is that Montezuma's Revenge has a mass of 4,700 kilograms, and the maximum height that the roller coaster achieves is 45 meters. So without friction, what's the maximum velocity of the roller coaster after achieving that height and rolling onto a straight and level track? Okay, so this This situation shows the law of conservation of energy because it shows the relationship between gravitational potential energy and kinetic energy. Again, we're working in ideal conditions without friction, so all of that gravitational potential energy will be converted to kinetic energy. None of it's going to be lost with friction and sound. So we can calculate the gravitational potential energy by taking mass times gravity times height, which we all know. It's 4,700 kilograms is the mass, gravity is 9.81 meters per second squared, and the height, which was stated as 45 meters. So we get 2,074,815 joules. And then we set that gravitational potential energy equal to the kinetic energy, since due to the law of conservation of energy, no energy must be lost. And for kinetic energy, which equals 1/2 mass times velocity squared, we already know the mass, so we can divide the mass and then multiply by 2, which leaves us with velocity squared. And then taking the square root of both sides gives 29.714 meters per second. So the maximum velocity after that 45-meter apex is 29.7 meters per second squared, or meters per second, its velocity. And that value also makes sense because we are not considering friction. The known maximum speed of the roller coaster is 25 meters per second, but that is in the real world with friction and energy loss due to sound. So the value being about 4 meters per second higher than the actual is completely reasonable. So the last situation we have involving the roller coaster deals with momentum and collision. So the roller coaster, which we know has a mass of 4,700 kilograms, is traveling at 25 meters per second along a level and frictionless track. And the roller coaster collides with a piece of metal of mass 100 kilograms. The final velocity of the roller coaster after the collision is 24 meters per second, so we need to find what the velocity of the piece of metal is after the collision. So here we have the roller coaster, it travels at 25 meters per second, hits this piece of metal, and then the roller coaster only slows down by 1 meter per second, so we need to find how fast this piece of metal is moving. So this situation deals with the law of conservation of momentum. Similar to the law of conservation of energy, momentum must be equal in the beginning and end of any interaction between two or more objects. So we have a net known momentum of the roller coaster that will equal the unknown momentum of the piece of metal. So we start by calculating the initial momentum of the system, which will just be the roller coaster. That's what RC stands for, because the piece of metal is at rest. It does not have any velocity. So we take 4,700 kilograms times 25 meters per second, and we get a system initial momentum of 117,500 kilograms times meters per second. And then we calculate the known part of the final momentum, which again will just be the roller coaster because we don't know the velocity of the piece of metal after the collision. So it's 4,700 kilograms times 24 meters per second, and we get a final momentum for the roller coaster of 112,800 kilograms times meters per second. So then we take the net momentum and set that equal to the mass times velocity of the piece of metal, which is the momentum of the piece of metal. So we take 117,500 minus 112,800 kilograms times meters per second, and we set that equal to 100 kilograms, the mass of the piece of metal, times the unknown velocity of the piece of metal. And once we subtract those two values and then divide by 100 kilograms, we end up with a final metal velocity of 47 meters per second. So that's the last problem I have, and thanks for watching.